Graphing a polynomial. So this entire video is dedicated to one example. We want to sketch the graph of this f of x. To do so is going to require many of the things we have learned so far. I suggest whenever you go to graph a polynomial, you dedicate a space to the results of all of the properties and tests that you do to just have one place allocated to the results you need, the properties and things we found out about this function to graph it. And we're going to start with the end behavior of polynomials. There's not a lot of work to show here, so we're just going to start to place the result straight into the box. We can see that this f of x has degree 4. That's an even degree. We can see that the leading coefficient is -2. That's negative. So we can conclude that the end behavior of this f of x is down and down. Next, we use our polynomial graphs and turning points. Any function will have at most n minus 1, so in our case, 4 minus 1 or 3 turning points. So when we go to sketch this picture, it will go from increasing to decreasing or decreasing to increasing at most 3 times. Next comes the longest part of these problems. We need to find the x-intercepts. To do so, we're going to factor f of x into linear factors. Always start by factoring out anything that all of the terms have in common. In this case, we can factor out a -2. Now I can turn my attention to the part in blue. The overall idea here is that I'm going to peel off linear factors from the function one by one. As I do so, it's the part I'm working on is going to get smaller and smaller. So this first step is actually going to be the longest. So I need to factor x to the fourth plus 3x cubed minus 12x squared minus 52x minus 48. This is where the rational zeros theorem comes in. If this function is going to have a rational zero, it's going to have to be a factor of -48 divided by a factor of 1. So I go and I list the factors of 48. Here's a warning. I've made a mistake here. If you're just in a hurry, you'll just list these factors. Be careful. Always include the negatives. They are also factors. So I have this long list now of possible rational zeros, and I need to find out if they are a zero. One way would be to plug it into the function, but as we're going to need to factor it out anyways, we're going to use the division algorithm and synthetic division to find these zeros. And I just start with what's probably going to be the easiest one on the list. Going to start with 1. Is 1 a 0? I apply synthetic division, bring the 1 down, multiply, add, multiply, add, multiply, add, and one last time, multiply, and add. I get a remainder of -108. This is not 0, meaning 1 is not a 0 of our function, which means we have not found a linear factor. So I'm going to take and cross 1 off the list. I try -1. It has a remainder of -10. So again, no luck. I try 2, remainder of -160. No luck. Things finally get interesting when I test -2. I get the remainder of 0. Meaning my function can be written as x minus -2 times 1x cubed plus 1x squared minus 14x minus 24. This is important. Return to where you were tracking how you were factoring f of x. -2 is a factor we pulled off of there. Now we've managed to turn the blue part, the degree 4 polynomial, into a linear factor times a degree 3 polynomial, which means now we can focus our attention on the degree 3 polynomial. So we start the process all over again. We apply the rational zeros theorem. For this cubic, it's factors of -24 over factors of 1. So we get the following list of possible rational zeros. Here's the nice part though. If 1, -1, and 2 were not factors of the degree 4 polynomial, they are not going to be factors of the degree 3 polynomial. So I don't need to test them. I do need to test -2 again, however. It could be a multiple zero. And sure enough, it is. So this cubic can be rewritten as x minus -2 times x squared minus x minus 12. Again, don't lose track of the factors as you take them away from the function. So now I've managed to remove a constant factor, -2, and 2 linear factors, leaving only the quadratic. No need to jump through all the hoops of rational zeros and things like that. In synthetic division, we have a bunch of tools for handling factoring quadratics. In this case, I can just factor it directly. As always, check your factoring. So at the end, I rewrite it. -2 times x plus 2 squared times x plus 3 times x minus 4. So I've taken f of x and written it as linear factors. Why do all this? Well, if you recall this really powerful list of 4 equivalencies that we had, x minus a is a factor. Well, now we have a list of factors. So a comma 0 is an x-intercept. We have a list of intercepts. Since x plus 2 is a factor of f of x, we get that -2, 0 is an x-intercept. Going to collect my thoughts on the table here. So the first intercept from this list, -2, 0, it has multiplicity 2. So the behavior at that x-intercept is a bounce or a touch. The graph is not going to go through that x-intercept, just going to touch it. The x plus 3 factor gives an x-intercept of -3, 0 with multiplicity 1. It will cross. The x minus 4 factor gives an x-intercept of 4, 0. It also has multiplicity 1, so it will be a cross. Place my table here in my all work box where I'm collecting everything I need. As one final piece of reinforcement here, I can use Descartes' rule and see that I should have gotten 1 positive real 0, which I did. So now I'm ready to graph. I'm going to begin by plotting my x-intercepts. Just as a matter of personal preference to help me when I get ready to graph it, when I go to graph -2, 0, it is an x-intercept, but I'm going to use an x to help indicate to myself that when I'm graphing this, I don't want to go through that point. I want to bounce or just touch it. I also have an x-intercept at -3, 0. I'm going to use an open circle here because I want to go through it. And my last x-intercept at 4, 0. Combine this with the end behavior of the polynomial as determined earlier. And now I'm ready to start sketching this function. Remember, this is just a sketch. The actual behavior between the x-intercepts may be different. So I'm going to start with my end behavior and go up to my first x-intercept. This needs to be a smooth, continuous line, and the behavior here is through, so I'm going to go through it. Next, I need to return because I have another x-intercept. This one, however, is a bounce, so I'm going to bounce off it. Travel on to my next x-intercept. This one is a cross, and it connects to the desired end behavior. Note the only places I touch the x-axis are at those x-intercepts, nowhere else. And I do have exactly 3 turning points here, and I could have at most 3. So this is a rough sketch of what this function looks like. A few things to note. Remember that complex zeros occur in conjugate pairs. While we didn't get to use that fact here, here's an example of what that could look like. Here's an f of x, and we are given that x minus I is a factor. Well, they are actually giving us 2 factors. Not only is x minus I a factor, but since they occur in conjugate pairs, because f has real coefficients, x plus I is also a factor. F of x is then divisible by x minus I times x plus I. So it's divisible by x squared plus 1. Synthetic division is really powerful, but that kind of makes it dangerous. It's so powerful it hides a lot of the inner workings. And it can cause people to use it when it shouldn't be used. It's very narrow in its application. This is a quadratic, so when I go to factor it out, I need to use long division. I can't use synthetic division. I mentioned it in the function that we did today, but don't forget to begin by factoring. In this example, this f of x, every term has an x. So we should always begin by factoring out an x. Remember, our goal is to factor this thing, so start with the easiest. As you saw before, chopping it down to size. The smaller the degree, the easier it is to factor. This factor of x leads to an x-intercept of 0, 0. This is the only factor that will lead to an x-intercept of 0, 0. It's a mistake we see quite often that the origin, uh, people just assume that that's an x-intercept. And it's probably because 0 is so special in a lot of these properties that we're using, but this is the only way you will end up with the origin as an x-intercept.